Hi, in this video I would like to take a deeper look at projectile motion. So when we talk about projectile motion, imagine, say, throwing a ball through the air. Now as the ball moves through the air, if we can neglect air resistance, which is there, but let's ignore air resistance right now. Imagine then throwing a ball through a vacuum. You're inside a huge seal off area and there's no air, and somehow you throw a ball, right? And so it's moving through, I was about to say through the air, but there is no air, right? So it's moving through space, I guess, no? And the only force acting on that ball as it moves is the pull of gravity. In other words, when we talk about projectile motion, we'll be making the assumption that the only acceleration that the ball experiences is downward. This means that as the object moves, and here we will assume it's moving in a plane, a two-dimensional plane, as it moves, its horizontal motion is uniform while its vertical motion is accelerated, which means if we throw the ball up through the air, like we throw it up like this, then you would expect that as it's going upward, it's slowing down. In other words, if you were to just look at its vertical motion, as it moves up, it would be slowing down, and then as it comes back down, it's speeding up. Look, notice all the while the velocity is decreasing, right? It starts out positive, and it goes to zero, and then becomes negative and more negative. So if the velocity is decreasing, we know the acceleration is negative, which means then that the acceleration must be pointing downward. Now horizontally, the velocity is constant. If you look up here, you see this little widget here. So what's going on here? What I have here is a counter. It's simply it's like a variable, and it starts at 0 and it increments from 0 to 10 in increments of 0.1. So it goes 0, 0.1, 0.2, and I have set it so that it takes 10 seconds to count from 0 to 10. And so in that way, I am able to simulate time. What I then do is I calculate the x position of this particle as a function of time. In other words, I treat this particle as a particle that's simply moving to the right, and I get the value of its x position for every point in time. Actually, I make the computer do that. I just give the computer the formula for position. So all I do is use the kinematic equations, right? So you know those, right? So for example, the position at the final position is equal to the initial position plus the product of the velocity and the time plus 1/2 the acceleration times the square of the time, right? And that gives you the position at some point in time. So when I say final position, I mean the position after after t seconds. We do the same thing for the y, and so the computer is constantly calculating the x and y positions and then updating the image on the screen. I also calculate the vertical and the horizontal velocities. Again, it's a simple little equation. The final velocity is equal to the initial velocity plus the product of the acceleration and the time. And I do so using the horizontal acceleration, which I've set to 0. I could also change this. So this little simulation I've made here it's a little bit flexible. I can give it some horizontal acceleration if I so want. But I've set the horizontal acceleration to 0, and I've set the vertical acceleration to minus 9.8. Alright? And so then you can see that at various points in time, I should maybe, let me just show the value. So you can see it's 2.4 seconds, right? And so notice, so what I'm doing, what I'm having the computer do is calculate the position, the x position, the y position of the particle, the x velocity and the y velocity. In other words, the horizontal and vertical velocities and the horizontal and vertical positions for each one of these. So the computer does this very quickly, right? The computer goes from 0 to 0.2 to 0.3 to 0.4 to 0.5 to 0.6 and calculates the positions and redraws the screen. So it does take some very significant computing power, which did not exist for mere mortals like myself when I was your age. Alright, and so then we can do that, and we can then simulate the entire thing. Alright. I can, with this software, get these values to automatically change. And so here it's called animation on. So if I put on the animation, what it does is just change the values of anything that I want, anything whose values I want to change. So here I want the value of t to change, and of course then I have all these dependencies set up, so as that value of t changes, then well, all those positions and velocities change. And so let's just do that so you can see it. There it is, right? Time is changing, and you can see the object moving through two-dimensional space. There is also a functionality referred to as trace, and what it does is whenever it calculates the position of the object, if I have the trace on, when it goes to redraw the screen, it leaves the previous image of that particular object. So I can put the trace on for this particular point, which is simply a point called P. And so let's bring that back here. And you can see where I'm doing it. I'm doing it off screen. I'm putting on the trace. And so when I animate this now and you see the animation, now you see the trace. And of course, that shape is a parabola. All right. I can also look at the more closely at the X and Y positions. So notice that before I do that, notice that as the projectile is going upward, this vertical vector here, the magnitude of this vector is getting smaller, while this vector is staying, its magnitude is constant, it doesn't change. And then here it approaches, it becomes 0, and then notice this magnitude is getting bigger again. Strictly speaking, it's, the scalar quantity is decreasing because it's going from what? Positive values, positive values to 0 and then to negative values. All right. So that velocity is decreasing as time goes by, which means the acceleration is negative. All right, so let's take a look at the position. So I've created like projection. So here, this is just the X position of the particle. Notice. So we can just focus now on the X position of the particle. No matter where the particle is, you see the X position, and we can also see the Y position. So now look closely at these projections, and you'll see that as the particle is moving, the focus on these, you'll see that this is traveling across at a constant speed, and then I'll do it again, and then you look at this one and see that this is going up but slowing down and coming back down. So you can't look at the two of them at the same time. So let's look at this one first. I'll put on the animation, and you see it's traveling at a fairly constant speed, right? Notice it's not going faster and it's not going slower. So look at this, right? Focus on that. Okay, let's redo this. This time look at the particle, the Y projection, right, as it goes upward. So focus on that. Remember, you can't focus on the two of them. Notice it's going up but slowing down, slowing down, slowing down, slowing down, and then it starts speeding up, back, coming back down. See it? To get some sense of that, perhaps to get a better sense of that, let me put on the projection for the X. Let me put on the projections, the trace rather, for the two of them. All right. And so let me put the animation on. All right. And let me try and stop it, but I can't. So, all right. So what do I want you to see here? Anyway, look at the spacing between these. Remember, what's happening is the computer is calculating the position and placing that image there. And normally it would erase the image so that you can see the object as moving. But here I left a trace, and so then you can see that whenever the position is calculated, the displacement from the previous position is the same. But here, no, notice the distance, the displacements that occur between one plot of the position and the other gets smaller as it goes up, which means that what it's traveling faster here, and then here what the projections, the particle, the images get overlapped, which means that what when it calculates the new position, we have a little circle now representing it, and so they're overlapping because it's slowing down. So you can see here that the particle is slowing down, and then of course it speeds up back all the way, and so these distances, then these little displacements here begin to get bigger, which means that in each little time interval where it's calculating the position, it has moved farther, which means then that it's speeding up. All right. Okay, so that pretty much covers what I wanted to talk about. Note that in this simulation here, we have the initial position of the particle at the origin, but in some problem that you're solving, the initial position may not be at the origin, or you can always place it at the origin, but it may be more convenient in a particular problem to have the initial position above the origin. No? So particle's initial position might maybe be here, no? And it may have zero vertical velocity. In other words, this particle might start out, moving totally horizontally, and then if the velocity is totally horizontally oriented, it will just simply go like this and come down, right? So I'll post this this little file for you so that you can play with it yourself. I'll put it up at geogebra.org, so head over there if you want to. There are many simulations there at geogebra.org, so I'm not getting any money from geogebra.org. I don't think they have any money to give anybody, but I really appreciate the software, and lots of teachers up there do a lot of great things now. Alright, so that's it for this one. Bye.